Okay, hello, welcome to the 1W-MINDS talk of Sjoerd Dirksen. It's my pleasure to have him and to introduce him to you. So Sjoerd studied math and economics and operations research in Rotterdam and in Utrecht. He then did a PhD also at the Technical University of Delft. And then he switched country to go to Bonn, first to the Hausdorff Center for Mathematics, and then he went a little bit closer back to home towards RWTH Aachen. And since April 2019, he is associate professor in Utrecht again. So thanks for agreeing to give this talk. I'm very much looking forward to it.
Thank you very much for the introduction, Karin, and thanks to all the organizers for organizing this seminar and allowing me to contribute here. It's a pleasure. So I'm going to talk about some joint work with Martin Gensel, who's currently my postdoc in Utrecht, Laurent Jacques, who is in Louvain, and Alexander Stollenwerk, who was Laurent's postdoc at the time when we did this research. So I'm going to talk about random neural networks, and I'm going to show that they have a new property that we discovered and described in our paper, which we call the separation capacity. Okay, so I guess if you haven't been living in a cave for the last few years, you have seen what a neural network is, but I'm going to go through the basics anyway to make sure we're all on the same page. In particular, this definition of random neural network is not really uniform. So let me tell you what I mean by that exactly. All right. So as we all know, a neural network is composed of layers. So I will call a layer L, and it simply takes the form of an affine function applied to an input, followed by an activation function, which is a real function that is applied element-wise to the output of this affine function. So n in will be my notation for the dimension of the input of a layer, and out the dimension of the output of the layer. And this output dimension is sometimes called the number of neurons because of the neurological interpretation of this model. Okay, so a neural network for me will simply be a composition of at least two layers of this form. So this means that we're going to look at feed-forward neural networks that are fully connected and have 1D input. So we're going to look at, let's say, a vanilla situation from a theory perspective. When I talk about the output layer of the neural network, I always mean the last layer of the neural net. And when I say something about a random neural net, what I mean is that this object, this neural net, is really a random object. So this means that all the weights, so all the elements of this matrix W here in every layer, and all the elements in this vector B, the bias vector, they're all random. Okay, in some works, random neural nets have a different connotation, and what is sometimes meant is that you have a neural network for which all the layers, except for the last one, so the output layer, are random, as we discussed before, but the output layer may be learned, so it may be adapted to a given data set. Okay, what is relevant for us today are only two possible activation functions. So the rectified linear unit, which simply takes the max of t and 0 of an input, or the sign function, which is also called the threshold activation function. So these are the only two activation functions that I will talk about. So if I talk about a ReLU neural network, all the activation functions in the network will be ReLU. If I talk about a threshold network, all the activation functions will be threshold functions. All right, so I think the first question that I should answer for you is, of course, we all care about neural networks because they are such powerful tools in practice for a range of tasks. However, studying random neural networks needs a little bit of motivation, I think. So there's one key motivation, namely that random neural networks are a key ingredient in deep learning, so in trained neural networks. because they're used typically as an initialization, right? So you initialize the parameters of a neural network at random, and then afterwards you run a descent type of algorithm to optimize the parameters using training data. And it is known that that this initialization is very important because it's a non-convex optimization problem that you're solving when you're training a neural net. And so a good initialization is a key contributor to the success. So that's one reason why people are interested in understanding what random neural nets are and what kind of properties they have. Okay, a second reason that they have been suggested to study, and this is taken from this paper by Sachse and others, is that they observed that you can use them for fast architecture search. So you can explore different neural network architectures for different tasks. And what they observed is that actually the hierarchy and the performance of the completely trained architectures quite closely follows the hierarchy of the architectures that have random weights, so that are left at their initialization. Okay, so what they suggest is to use random neural nets to explore different architectures. Okay, and then finally, random neural nets are also explored as a computationally cheap alternative to fully learned neural nets. So training a neural network, if you've done it, you know it's time consuming, so it takes a lot of computational power, but also human labor, right? It's eternal parameter tuning. And therefore, people have also looked at simply simpler methods where you leave most of the network at random. So specifically, all the layers except for the output layer are left at random, and you only use training to determine the output layer of the network. So what this amounts to, if you view it differently, you're pre-processing the data with a random neural net, and then afterwards you apply a linear method. So for example, I'm going to talk about binary classification as a learning task. So in that case, you would apply a linear classification method to that pre-processed data. And that already gives surprisingly good results. So there are many experimental works in that direction. So this is also something that is interesting to understand. Okay, so I don't want to overstate what this does here. There's of course a substantial performance gap between this type of method, so pre-processing with a random neural net and using linear classification as opposed to a fully trained neural net. Okay, so what I would like to do is give you an overview of two interesting properties of random neural nets that have been studied recently. So their approximation power and their memorization capabilities. And then afterwards, I want to introduce a new capability that neural networks have, namely the separation capacity. And this last property that I'm going to introduce has very much to do with understanding this. So understanding what pre-processing data with a neural network really does. So what the output of that operation will look like. Okay, so let's first talk about approximation capabilities. So I'm going to talk here about so-called RVFL networks. So this is a class of neural networks that has one random hidden layer and then a learned linear output layer. And what turns out is that this class of neural networks has satisfies the uniform approximation property. So there's a classical result in this direction by Igalnik and Powell from 95. And a bit informally stated, so I'm leaving out some conditions here to not make it too technical. But the gist of it is the following. So you can approximate any continuous, compactly supported function on RD, taking values in R, with RVFL networks arbitrarily well, as long as you make them big enough. So if you make this hidden layer of the network wide enough. Okay, so there are networks Fn, where Fn has n neurons, such that in the limit, you get a zero approximation error, and the approximation error is measured as the expected L2 approximation error. So this is a classical result. And then more recently, people have studied high probability quantitative versions of this result. So I'm citing here a work that is coming from the MINDS community, I would say. So Diana Needle and several co-authors, including my colleague, Palina Salanevic. And what they proved is the following. So if you fix an accuracy epsilon, and you let a number of neurons exceed 1 over epsilon times a log factor times some constant that will depend on the dimension. So I will say a little bit more on that in a minute. Then you can find an RVFL network, Fn, such that this L2 error is smaller than epsilon with high probability. Okay. Okay, so there's a catch in this approximation result. So it looks very cool as I stated now. However, this constant that you see here, CD, grows exponentially in D. So there's a curse of dimensionality taking place here. And unfortunately, this is also a fact of life. So there's a more recent work by Daniel Su and some co-authors where they study approximation problems for Lipschitz functions on the continuous cube in RD. And they get matching bounds for this approximation problem. And in particular, their lower bounds show that this exponential dependence is really a fact of life. So there's not much that you can do about it. Okay, so this will be important as a comparison for the results that I will be stating later. Okay, so now let's talk about memorization capacity of random neural nets. So this has to do with the following memorization question. So if I'm given some training data, so some data x1 up to xn in RD, and some arbitrary labels y1 up to yn. The question is whether I can find a small neural network, let's say, with a given prefixed architecture, such that I can get an exact fit on the training data. So this property is called memorizing the training data. And what some recent works have shown is that you can solve this problem with a neural net with random hidden layers and a learned output layer if the data is delta separated. So the minimal distance between data points is at least some delta, let's say. And these results are quantitative and depend on delta. So I will state one in detail because it's relevant for what I'm going to talk about later. So this is a result by Bressler and Nagarai from 2020. And they show that you can do it with a neural net with one random ReLU layer. And this layer has a number of neurons that scales roughly like the number of points that you would like to memorize, up to a polynomial factor in terms of the log of the number of points and 1 over this separation parameter. There's also a very nice work by Roman Verschinin, who looks at this memorization question and shows you can solve it with neural networks that have 2 random threshold layers. So these threshold activations are a bit more challenging. So this is a bit more challenging result. So I won't discuss this in details. This won't be relevant for what I'm going to discuss next. Okay, so now let's talk about separation capacity. So what I've learned in my very first presentation course as a student is that people can take very little information out of a talk, essentially only one thing. So if there's anything that you're going to remember from this talk, then please let it be this picture, which illustrates the separation capacity. So I will explain it in detail in a minute with really quantitative results, but the situation is as follows. So I'm going to look at a situation where I have 2 sets, x minus and x plus. And what I invite you to think about is a situation where you have a data generating distribution where this x minus corresponds to points that will have label minus, and these points in x plus will have label plus. And they are kind of entangled in space. And the only thing that we're going to know about it is that these sets with plus and minus labels, they're going to be delta separated in the sense that I just discussed while I was discussing memorization results. And what I'm going to show is that a particular neural network, a random neural network F, has the capability to make these two sets linearly separable. Okay, so if I apply this random neural network, then with high probability afterwards, the situation will look as follows. So all these points that correspond to minus labels will be mapped here, and the plus labels mapped here. And I can linearly separate these two sets with a hyperplane. And I will also have some control over the margin that this separating hyperplane has. Okay, so I'm going to make a quantitative statement in a minute. And in particular, the answer to this separation question will depend on various parameters. So let's go through this slowly in some steps. Okay, so let me first reiterate what I just said. So I'm going to look at two delta separated sets, x minus, x plus. So the minimal distance between a plus point and a minus point is at least delta. And this map F is a map from RD going to Rn hat, and it's going to be a random neural net. I'm going to specify it in a minute. Okay, and the questions that I would like to answer are the following ones. So when can this random neural net make the two sets, x minus, x plus, linearly separable with high probability? And a more refined version of that question is to ask also for a lower bound on the induced separation margin mu that you see depicted here in the picture. Okay, so just to be sure, so what I want is that after I map all my data with this random neural net, so I'm not doing any learning, right? So let's have that clear from the start. But what I want is that after applying this random neural net, my data is such that I can find some hyperplane, which has a direction vector u and a shift tau, such that it is not only true that the image of the minus points and the image of the plus point lie on different sides, but also that I have some margin. So what you get here is that the inner product between f and x minus and plus tau should not only be negative, but I want to have a little bit of margin. It should be smaller than minus mu. And a similar thing for the plus points. Okay, so this is what I mean by margin. Okay, so why am I interested in getting bounds on the margin? So this has to do with the generalization theory. So for example, if I now want to apply learning, I could, for example, now do binary classification by applying hard SVM to this transformed data set to find the maximal margin hyperplane that separates these two transformed sets, and classify my data in that way. And generalization error bounds for such a procedure can be phrased in terms of the margin that you have here. So the larger the margin you have, the smaller the generalization error will be. Okay, so I won't detail this in this talk. So this is a well-known statistical learning theory. Okay, so now let me tell you what this map F looks like. So this random neural net that can make my data linearly separable. So it will be a network with two random ReLU layers that have the following form. So I will refer to them later on the talk as simply as random ReLU layer, but they have a specific form. So there's a parameter attached to each layer. So it's called lambda for the first one, lambda hat for the second layer. And each layer has the following form. So it looks like a ReLU layer, and there's a normalization factor in front here. So we're normalizing by √2 over the output dimension. And it's a random layer. And the weights in the weight matrix will all be IID standard Gaussian. So this is going to be a standard Gaussian matrix. And B, the bias factor, is going to be uniformly distributed over this interval from minus lambda to lambda. So this lambda is really the maximal bias that can occur. And moreover, B and W should be independent. Okay, so yeah, we use this layer for theoretical purposes, but after we finished our analysis, we were of course curious whether this particular initialization is also used by practitioners, and it appears that the closest popular initialization that is used in practice is the so-called He initialization. Which stems from this paper, which has I think 4 authors, but it's only named after the first one, unfortunately. So it's close to what I'm writing here. The only difference is that there's no bias in the He initialization, and typically this N out is replaced by the input dimension. But that's one that is often used. So that's pretty close. Okay, and now this random neural network that I'm going to look at, and which will have this separation capacity, is going to be a composition of 2 of these layers. So both random ReLU layers, so they both have their own bias parameter, and they look a bit different. So the first layer will have a relatively small output dimension, let's say, and this second layer is going to have a large output dimension. Okay, so if you want to think about the neural network in terms of a diagram, it will grow a little bit, let's say, in the first step, and then become outsized at the final step. Okay, and these layers, they should be independent for what I'm going to tell you next. Okay, so now we've discussed most of the specifics of this question. So just to recall, we have 2 delta separated sets. I've now specified what kind of random neural net I'm going to apply to these 2 sets. And I want to figure out when this random neural network will make x minus and x plus after transformation linear separable with high probability. And what I want is to get some guarantees on the margin that is achieved after applying this transform. And something that I would like to emphasize here is that what we are looking for are instance-specific guarantees. So what we will see later on, so I can already say this, is that in a worst case, this output dimension n hat will have to be very large. So there will be a curse of dimensionality appearing that is similar to the curse of dimensionality that exists in approximation properties of random neural nets. However, if these sets x minus and x plus have some low complexity structure, then this problem may not occur at all. Okay, so what I want to get are what are called instance-specific guarantees. So I want to say something like if the size of the first layer exceeds some factor and the size of the second layer exceeds some factor, then the separation margin will exceed a certain threshold. And these factors that I write here, they should be formulated in terms of so-called complexity parameters that describe how difficult this separation problem really is. Okay, so this is what I'm going to do next. Okay, but to parse everything for you, I'm going to do it in 2 steps. So I'm first going to look at a scenario that's a lot simpler, where x plus and x minus consist of finitely many points. And then afterwards, I'm going to go to the general setting that I'm really interested in, right? So we think of x minus and x plus as being the support of a data generating distribution. So I would like to solve this problem really for infinite sets. And that's what I'm going to do afterwards. Okay, so let's first do some warming up. So the people in Europe are barely awake, so this is, I think, a good thing to do. So let me first show a statement for finite sets. So remember, x minus x plus, they are delta separated. I'm going to denote the number of points in the first set by n plus, the number of points in the second set by n minus. And F is going to be this two-layer random ReLU network that I discussed in detail before. Okay, and now we should do the following. So the maximal bias of the first layer, so that's lambda, it should scale roughly like the radius of these two sets. So these two sets will be contained in a unit ball in this first statement. And the maximal bias should correspond roughly to this radius of this ball that the sets are contained in. You should think of it like that. It should actually be a little bit bigger for technical reasons. The size of the first layer should scale like roughly like the log of the number of points that you have. Okay, so that's written here. And there's a factor here in front that I will hide. So there will be some factors C0, C1, etc. They're going to be rational functions of the parameters that are stated here. In this case, it will be a polynomial in lambda and 1 over delta. So 1 over the amount of separation that I have in this problem. Okay, the second layer will have to look as follows. So the maximal bias of the second layer should exceed some factor alpha. And in this result for finite sets, this factor alpha will be the root of the log of the number of points that I have in the plus set that you can think of as corresponding to positive labels. The number of neurons, so the width of the second layer, has to scale like, well, log of the number of points. That's in the minus set. That's not very important. The more important factor is a factor theta. And this theta will scale like, again, a rational function in lambda and delta times alpha squared. So this alpha that you see here, and then the exponential of that. Okay, I'm writing it in this funny fashion so that we can more easily discuss the general result later. What this means in this setting for finitely many points, it means that the size of the second layer should be as large as a low-order polynomial in terms of the number of points in this plus set. Okay, so it's m plus to the power C3. And C3 is a polynomial in lambda and 1 over delta. Okay, if all these conditions are satisfied, then with high probability, after applying this random neural network to these two sets, x minus and x plus, they magically become linearly separable with a margin that scales like 1 over theta. Okay, so that's the statement that I can make for finite sets. So personally, I think this this property, this separation capacity is a very nice property, and to me, it's kind of surprising, right? So remember, you're not doing any learning here. These sets x minus x plus, they can be pretty arbitrary. They have to lie in some ball, and they should be delta separated. But then if I apply some random neural network with two layers to it, then suddenly after transformation, the geometric arrangement looks very nice. So they become linearly separable. All right. So to see how good this result is, because personally, when we did this analysis, I was a little bit worried about this exponentially scaling factor. That appears in a result, and I was a bit worried that we were doing something trivial. So to see that this is not the case, I would like to connect back to the memorization problem and to compare it to the results that we have here. The reason that there's a connection to the memorization question is as follows. So let me first recall the memorization problem. So this question is as follows again. So if you're given some data set with some binary labels, and these can be arbitrary, the memorization question is whether you can find a small neural network from a class that corresponds to a particular architecture, such that you can memorize this data set. So you can fit these labels exactly. And what we get as a direct corollary of this separation result is a method to find a memorizing network. And it's very simple. So you should first apply this two-layer random neural network F to this data, and then afterwards find a separating hyperplane. And since the data is linearly separable, you can even use hard SVM to do that and get a perfect solution. So that will return a memorizing neural network, which has now 3 layers, right? So this output layer will correspond to this separating hyperplane. This will happen with high probability. So there's a small probability that it may fail, but it's exponentially small. And this happens if all the conditions of the previous theorem are satisfied, right? So, but I'm only going to single out one condition that corresponds to the size of the second hidden layer of this memorizing network. So it should scale like a polynomial in terms of the number of points. Okay, so this is not a state-of-the-art result. Let me emphasize that, because we've already seen something in that direction. So we've already seen that one can achieve memorization with a network with maximal width that scales like the number of points instead of polynomial in terms of the number of points. However, I was relieved when we sort of figured this out, because it shows that this result is sort of a fact of life. So this exponentially scaling factor should be here. So this shouldn't be too far off from the truth. All right. So this is the simple situation with finitely many points that we're not really interested in. So now let me get to general sets. So what I'm going to do is now introduce first 2 complexity parameters that I will use to describe the complexity of the initial data arrangement. And then show how this statement for finite sets, the separation capacity for finite sets, can be generalized using these complexity measures. All right, so just to recall, this is the problem that we want to solve. So now x minus x plus are infinite sets. I'm going to apply the same random neural network to it as we studied before when we were studying finite sets. And I want to figure out when this picture that I have on the right is true with high probability. Okay, and to describe how complex this situation on the left is, I'm going to use some classic parameters from high dimensional probability. So let me go through them just to make sure, in case you're not familiar with these parameters. So let x be some set in RD. So one complexity measure that I'm going to use is the epsilon covering number of the set, which is in words simply the smallest number of balls with radius epsilon that you need to completely cover the set. The second parameter that I'm going to use is the Gaussian mean width of the set, and it is defined as follows: as the supreme over all x and x of the inner product with some standard Gaussian, and you take the expected value afterwards. Okay, so if you're not familiar with these parameters, then don't worry. So I invite you to think of the following situation, where x is the intersection of a low dimensional subspace of dimension k and the Euclidean unit ball, let's say. Then this covering number will scale like c over epsilon to the power k. In particular, if you take the log of this, it will scale like the subspace dimension roughly, and this Gaussian width will scale like root k. Okay, so let's keep this example in mind if you're not familiar. So I have a picture here to give a geometric interpretation of the Gaussian width, but looking at the clock, I'm going to skip this and go directly to the statement, the main theorem that we have for general sets. Actually, we have even a bit more refined statement, but I decided that this would be a bit too much for today. So let's look at this one. So we have now two infinite delta separated sets. And instead of looking at the number of points in these sets as we did before, which is now infinite, I'm going to replace these two parameters that we had before, n minus and plus, which were previously the number of points in x minus and the number of points in x plus, by covering numbers corresponding to a certain radius. Okay, so what this radius is maybe not so important for the moment. This is simply what comes out of the analysis. F is going to be the same two-layer random ReLU network that we used before. The first layer will have a similar architecture. So the maximal bias of the layer will scale roughly like the radius of this ball that x minus x plus are contained in. The size of that layer will need to be as large as d. It will have to scale also like we had before. So like the log of the n minus times n plus. In addition, it has to be larger than the sum of the squared Gaussian widths of these sets. Okay, so if you remember this example where you look at k-dimensional subspaces, then what is written here in brackets is roughly k. Okay, so that's what you can think of. So in that case, this the size of this layer should be roughly the input dimension. So it's like a flat layer. Okay, the second layer of the random neural net will have to be a lot larger in general. So the maximal bias of this second layer now has to scale like the sum of the Gaussian mean widths of the two sets. So that was previously it was the root of the log of the number of points with plus label that we had. And now it's this new parameter. And the size of the second layer has to scale as before. And the only thing that changes is how this theta parameter is formulated. So it's again an exponential in terms of alpha squared, where this alpha is now as written here. Okay, so thinking again about k-dimensional subspaces intersected with the Euclidean unit ball, this factor alpha will be like root k, and this theta will scale like e to the k. Okay, so exponentially in this subspace dimension. So this already tells you that if you're in a very bad case where you have not subspaces but some full dimensional sets, then this parameter is going to scale exponentially in terms of the dimension. So you have kind of a curse of dimensionality here. But the benefit of this instance-specific statement that I'm stating here is that it shows that if these sets have low complexity, then this curse of dimensionality may not take place at all, right? So if you think about I don't know, one-dimensional subspace, then this factor is not so bad. Okay, and the conclusion is the same. After applying this random neural network to the two sets, I get a nice geometry afterwards, namely two linearly separable sets, and I know something about the margin. It will scale like 1 over theta. Okay, so this is the main statement that I wanted to present today. So I'll have a brief look at the clock. So I think we have some time left to also look at the proof. So I will try to give some geometric intuition about why this is true. So I will show you a lot of pictures. Okay, so first, the proof relies on two new results. So I included them in the slides at the back, but I don't think I can discuss them in detail. So these are two properties of, so the first one is a property of random ReLU layers that is new and I think interesting in its own right. So what we show is that a random ReLU layer of the form that I discussed before, so with Gaussian weights and a uniformly distributed bias, kind of acts like a Johnson-Dinner-Strauss embedding on infinite sets. So it will approximately preserve Euclidean geometry. So inner products between vectors, and also for the story that I'm going to tell next, Euclidean distances between points are also approximately preserved. And not completely as in the JL embedding, so it's only for nearby points, but let's think of it in this way. The second result that may be of independent interest is a hyperplane separation result, where you draw, where you have two sets and they are linearly separable, and you ask for a lower bound on the probability of separating these two sets with a randomly drawn hyperplane, where the direction is Gaussian and the shift is uniformly distributed. So we have a lower bound for that probability, and that's also an important ingredient for the proof. We will see in a minute why. Okay, so now let's sketch the proof. So what I'm going to do is look at a special case where the two sets that I'm going to transform are unions of some Euclidean balls that may be arbitrarily arranged in space. So they can be entangled as in this picture. And so X minus is going to be the union of XL minus. Each XL minus is a little Euclidean ball, which has a center CL minus and a small radius R. So it should be small enough. I will get to that in a minute for the story that I'm going to talk about. And these XJ plus are going to be the red balls. Okay, so the situation is that we have some union of balls. They're arranged. They correspond to different labels, and the balls corresponding to different labels should be at least delta separated. Okay, and now recall I'm going to apply a composition of two random ReLU layers to this set. And the claim is that if these two layers are wide enough, let's say, then what I should end up with at the end is a disentangled situation, right? So these blue balls will be mapped into something. These red balls will be mapped into something, and these two somethings will be linearly separable. And the proof is via a two-step procedure. So what I'm going to show is that the first random ReLU layer sort of establishes a nice geometrical configuration, and the second layer exploits the configuration and achieves linear separability. So I'm going to discuss the actions of these two layers separately. So let's first look at the action of the first layer. Okay, so let's look at the first layer applied to X and then the ith coordinate of that. So that looks like root 2 over n times the ReLU of the inner product of WIX. So WI is the ith row of the weight matrix, and BI is the ith coordinate of the bias vector. Okay, so what will be important for what I'm going to explain here is that there's some hyperplane geometry associated with the action of such a random ReLU layer. Okay, so this what you see here, WIX plus BI, if this is the points for which this is equal to 0, that will simply be a hyperplane in space. So it's drawn here in this picture. So this WI will be the direction vector. This BI is a certain vector that determines the parallel shift of the hyperplane. And this ReLU gives you well, the following information. So if the point X is not on the hyperplane but on the left, then this ReLU will output 0. And if it's on the other side, you get a bit more. You get a positive number out that sort of also gives some information on how far this X is actually located from this hyperplane. Okay. So as a first step, what we show is that for every pair of centers of the balls, So here's a center for a minus ball, a center for a plus ball. So for any pair of all of these centers, sorry, I have to say it the other way around. With high probability, for every pair of these centers, there's a large fraction of hyperplanes that will separate these center points. That's the first thing that we show. Okay, so let's take that for granted. And for the coordinates corresponding to such separating hyperplanes, you can say the following. So these coordinates for I that correspond to these separating hyperplanes, if you look at phi applied to a center of a minus ball, it will be 0. If you look at the first layer applied to the center of a plus ball, it will be bounded away from 0 by something that looks like delta over root n. Okay, a consequence of this, and this is kind of an algebraic calculation, is that that there exist hyperplanes which separate the image of any center corresponding to a minus ball from the set of the images of all plus centers. So C plus here, large C plus, is the collection of all centers corresponding to plus balls with a certain margin. Okay, the number is not so important. But what this means geometrically is that after applying this first layer, I have the following situation. So you can imagine all these centers corresponding to the plus balls lying in the middle here. And then all these centers of the minus balls after transformation sort of lie as satellites located around this big clump in the middle corresponding to the plus centers. Okay, and you can make hyperplane cuts between all these satellites and the stuff here in the middle. So that's the nice geometric configuration that is achieved after one layer. And actually, it's even better because what we also know, thanks to this, this fact that random ReLU layers approximately preserve distances, is that this picture will not only be true for the centers of the balls, but actually for the entire balls. Okay? Under the condition that that the radius of these balls that I'm looking at is small enough. Okay, so let's take that for granted. And if we do that, what I get after the first step is the following configuration. So the union of the plus balls is mapped to some clump in the middle, and then the images of the minus balls form satellites around this big ball in the middle. So that's what you get after one step. Okay, so now let's look at the action of the second random ReLU layer, which has the same form. Okay, so what we show with our hyperplane separation result is that the hyperplane corresponding to one coordinate of this ReLU layer will separate one of these images of a minus ball from the big clump in the middle here with a certain probability, PT. Okay, and you get a certain separation margin here, T. So this this probability of separating will depend on this separating margin here, and this probability I'm not going to specify it here. You can find it in the paper. This will be a very small probability actually. So it will look like something that is exponentially small. However, this is only true for one hyperplane. And if I look at the action of the entire second ReLU layer, then I have many of these hyperplanes. So if I look at the effect of the entire transformation, then I can use simply a Chernoff bound and a union bound to actually show that with high probability for any of the images of one of these minus balls, there is actually a larger number, so PT, the probability of separation for a single hyperplane, times the number of hyperplanes that I'm drawing, that will separate this big clump in the middle from this transformed blue ball that is above there. Okay, so if you take a large number of hyperplanes, or thinking in terms of the ReLU layer, a ReLU layer of a large size, then I get a lot of hyperplanes that separate these. Okay, and again, a sort of algebraic consequence of this, which I won't detail here, is that then the transformed sets, which will correspond to the entire neural network applied to the plus balls, and the entire neural network applied to the minus balls, will become linearly separable with a certain margin that will depend on this PT. Okay, and this what you see in this argument, since this PT is this separation probability for a single hyperplane is rather small, this explains why you have to take quite a large second layer in the network to get this linear separability. Okay, so I think I should finish up. So I'm going to skip this data preservation result, this Johnson-Lindenstreit type of result for random ReLU layers, and also this second tool that I refer to, so the random hyperplane separation results. So I think if you're interested in it, you can find this in the paper. So in general, so I think you probably have had enough after the talk. But if you can't get enough, then please simply go to archive, and you can find all the details of the proof, and also these two nice tools that we're using over there. Okay, so with that, I would like to thank you for attending, and I'm happy to take questions.